First question is, a geostationary satellite is orbiting the Earth at a height of 5r above the surface of the Earth, where r is the radius of the Earth. Geostationary satellites are the satellites which are stationary with respect to Earth. That means these have the time period 24 hours, as Earth revolves around its axis in 24 hours. Using the Kepler's third law, we know that t square is proportional to r cube. So this implies that for geostationary satellite, 24 square is proportional to, and radius of the circular path for the satellite which is at a height 5r will be 6r. 5r plus r is the radius of the Earth. So it is 6r raised to power cube. This is the equation number 1. The time period of the another satellite in hours at a height of 2r from the surface of Earth is, suppose it has the time period t, so it is t square, and now it is proportional to height is 2r and radius of the Earth is r. Therefore, distance of the satellite from the center of the Earth will be 3r. So it is 3r raised to power cube. So it is equation number 2. Now dividing the equation number 2 by 1, we will have t square by 24 square, that is equal to 3r by 6r raised to power cube. So it is equal to 1 by 2 raised to power cube or 1 by 8. Therefore, t square is proportional to equal to 24 square by 8 or 24 into 24 divided by 8, cancelling by 8 it will be 3 or 72. Therefore, t will be equal to square root of 72 or it will be 6 root 2 hours. So option C is the correct option. Second question is, if VE is the escape velocity and V naught is the orbital velocity of a satellite for orbit close to the Earth's surface, then these are related by. For orbit close to the Earth's surface, H is approximately 0, or we can say H plus RE is approximately equal to RE. And for this condition, the escape velocity is square root of 2g RE and orbital speed is root g RE. Therefore, we can say that escape velocity is the root 2 times of the orbital speed. So option D is the correct option. Next question is, a ball is dropped from the spacecraft revolving around the Earth at a height of 120 km. What will happen to the ball? Here, ball and the spacecraft is a single system and there is no external torque. So we can say that external torque is 0, and because torque is the rate of change of angular momentum, so this is 0, that means angular momentum is constant. This implies that angular velocity is constant. So ball will continue to move around the Earth with the same angular speed. So we can say that it will continue to move with same speed along the original orbit of the spacecraft. So option C is the correct option. Fourth question is, the radii of the circular orbits of two satellites A and B of the Earth are 4r and r respectively. If the speed of the satellite A is 3v, then the speed of the satellite B will be. We know that orbital speed of a satellite is v0, that is equal to root gme by re plus h. So for satellite A, the orbital speed is given 3v. For satellite B, we have to find the orbital speed, while the radius of the orbit, that is re plus h, for the satellite A is given 4r, while the re plus h for satellite B is given r. So using the formula, we can write that orbital speed of B divided by orbital speed of A, that is equal to the square root of gme divided by re plus h of the satellite B divided by root gme by re plus h of the satellite A. This implies that we have to find the orbital speed of satellite B divided by, and orbital speed of satellite A is given 3v, that is equal to, here gme get cancelled and we can write it is re plus h for satellite A divided by Re plus H for satellite B. And these values are given. For A it is 4R, and while for B it is given R. So R and R get cancelled and square root of 4 is 2. Therefore, orbital speed of the satellite B is equal to 2 into 3V, that is equal to 6V. Hence option B is the correct option. Fifth question is, for a satellite moving in an orbit around the Earth, the ratio of the kinetic energy to potential energy. We know that potential energy of a satellite around the Earth is given by minus G mass of Earth into mass of satellite divided by the radius of the orbit, and kinetic energy is given by G MEM by 2R. Therefore, magnitude of potential energy is equal to twice of the kinetic energy, and the ratio of kinetic energy with potential energy is equal to 1 by 2. Hence option A is the correct option. Sixth question is, the satellite of mass m is orbiting around the Earth in a circular orbit with a velocity v. What will be its total energy? We have already found that orbital speed of the satellite around the Earth in a radius of orbit r is root gm by r, where r is equal to Re plus h. Potential energy is minus g MEM by r, and kinetic energy is half of g MEM by r. So total energy, which is the sum of the potential energy and kinetic energy, will be equal to minus g MEM by r plus half g MEM by r, and this will be equal to minus half g MEM by r. Now we can apply the formula of the orbital speed for g me by r, and this is square of the orbital speed. So we can write total energy is minus half m v0 square. That is, it is the negative of the kinetic energies. Hence, option D is the correct option. Next question is, the main radius of the Earth is r, and its angular speed on its own axis is omega, and the acceleration due to gravity at Earth's surface is g. What will be the radius of the orbit of geostationary satellite? Geostationary satellites are stationary with respect to the Earth. That means their time period, that means their angular speed are same as that of the Earth. So using the concept of centripetal force, which is mv square by r, this can also be written as m omega square r, because v is equal to omega r, and it will be the provided by gravitational force. This is g into mass of Earth into mass of satellite divided by the square of the distance between the Earth and satellite. So we can say that m and m get cancelled. Therefore, omega square is equal to g me by r cube. Using the formula of acceleration due to gravity, the g, this is equal to g me by r square, where r is the radius of Earth. Therefore, g me will be equal to gr square. Substituting the value, we will have omega square equal to gr square by r cube. We have to find the radius of the orbit. So r cube will be equal to gr square by omega square. So r will be equal to gr square by omega square raised to power 1 by 3. Hence, option A is the correct option.